Today's lesson will be on functions. This is section 1.4 in your textbook. The essential question for this lesson will be, when is a relation a function, and how do you find the domain of a function? So initially we're going to have to understand some definitions here. The first is going to be, what is a relation? A relation simply explains how two quantities are related to each other. In mathematics, we can have equations or formulas which represent these relations and can be used to take and show what exactly a relation is. Okay? Now, a function is a special kind of relation that matches each item of one set with exactly one item of a different set. Now, the key thing about this definition is the term exactly one, okay? That's the key term here, that we have a relation that matches one item, each item of one set with exactly one. That means one and only one item from another set. You can't have a function match one item from one set with two items from a second set. It has to be a one-to-one relation. Now, to understand this definition a little better, let's assume we have two sets. We've got one set A, which consists of the numbers 1, 2, and 3, and we have a second set B, which consists of the numbers 4 and 5. All right, so a function says that it is a type of relation that matches each item from one set, in this case set A, with exactly one item from set B, or in other words, one and only one item from set B. So we could say that, let's see, how do I want to do this? We could say that from set A, 1 would correspond to 4. Okay, 2 would correspond to 5, and we could even say that 3 corresponds to 5. But we don't have a situation where, say, 1 would correspond to 4 and 5, or 2 would correspond to 4 and 5. Each item in set A corresponds to one and only one item in set B. Okay? So we could have two items in set A correspond to one item in set B, but we could never have one item in set A correspond to two items in set B. Now, to better understand this, set A is going to be referred to as the domain, while set B is going to be referred to as the range. So now we can change our definition to say that a function is a special kind of relation that matches each item from the domain with exactly one item from the range. Now, there are different ways you can represent a function. On the previous page, I showed a function represented by showing the actual sets. I could also have shown that in the form of a table, where I could say that, okay, we have set A, and we have set B, and we make ourselves simply a table where we've got set A had 1, 2, and 3 in it. 1 from set A corresponded to 4 from set B, 2 from set A corresponded to 5 from set B, and 3 corresponded to 5 from set B. Now, this would be a function. Now, we could similarly have a table. Say I had a table like this, where I had A and B. And let's say we still had 1, 2, and 3 in set A. Okay. And let's say 1 corresponded to 4 in set B. And also corresponded to 5 in set B. And 2 corresponded to 5, and 3 corresponded to 5. Well, notice 1 corresponds to both 4 and 5, so therefore this is not a function. Okay, similarly, I could show it graphically. Let's say we had a graph. And we got a y-axis and an x-axis. And let's say we had a point here, a point here, and a point here. Now, for each value of x, and x is, this case, is going to be the domain, there is only one value for the range, where these red dots are. The range would be the y value. So this would be a function. However, let's say for this value of x right here, and I'll just put an x there, let's say that one value is y equals 0, but we also have another value, y equals minus 1. Well, then that becomes not a function, because for each value of the domain, I've got 2 values for the range. So that would not be a function. So now let's look at equations and see if we can determine whether a particular equation is a function. So say we have 2 equations here. We have one equation, x squared plus y equals 1, and another equation, minus x plus y squared equals 1. Okay. In each case, we're going to solve the equation for y. So in the first case, we end up with y equals 1 minus x squared. Well, if you think about this, for each value of x, you end up with a single value of y. You never come out with 2 different values of y for a single value of x. So the equation on the left is a function. So now on the right, if you solve that, you end up with y equals plus or minus the square root of 1 plus x. Because first you solve for y squared, you get 1 minus x, 1 plus x, and then you take the square root of it, and obviously when you take the square root, you can have plus or minus. So in this case, for each value of x, you're going to come up with 2 different values for y. One's plus, one's minus. Therefore, the equation on the right is not a function. Now let's go back to the equation on the left, which we said was a function. We do have a means for naming functions, and this is known as functional notation. So rather than write the equation on the left as y equals 1 minus x squared, we might consider writing it as follows. F of x is equal to 1 minus x squared. Now this can be read as either, the f of x portion can be read as either the value of the function at x or simply f of x. So the symbol f of x corresponds to the y value for a given x. Now one thing to keep in mind is that f is the name of the function, and f of x is the value of the function at x. For example, if we were to say f of 2, that would mean the value of the function f at x equals 2. Or 1 minus 2 squared, which is simply equal to 1 minus 4, or simply minus 3. So the value of function f at x equals 2 is minus 3. Now, in calculating the value, we don't always have to have a number inside the parentheses. For example, using the same function f, I could say, well, what is f of t equal to? Well, if I plug in t for x, I would get 1 minus t squared. Or if I said f of x minus 1, that means I would, every place in the original function where I had an x, I would substitute x minus 1. And that would simply yield 1 minus the quantity x minus 1 squared. Now we will talk about a different type of function, and this is called a piecewise function. And this is a function defined by two or more equations over a specified domain. So we might call it a piecewise defined function. For example, we might have a function, f of x, which is equal to x squared plus 1 for all values of x less than 0, in other words, negative values. And it might be equal to x minus 1 for all values greater than or equal to 0. So this would be a piecewise function. So if we were to evaluate this function at minus 1, in other words, try to determine the value of f of minus 1, we would plug in minus 1 into the first equation. So we would have minus 1 squared plus 1, which is the same as 1 plus 1, or 2. So f of minus 1 would equal 2. So what if I had f of 2? I'd want to know the value of the function at x equals 2. Well, in this case, 2 is certainly greater than or equal to 0, so I would use the second equation. And this would be equal to 2 minus 1, or 1. So f of minus 1, we'd use the first equation and come out with f of minus 1 equals 2. F of 2, we'd use the second equation, and we'd come out with f of 2 is equal to 1. So let's now discuss a little bit more about the domain of a function. Now, the implied domain of any function is all real numbers for which the expression is defined. So in our previous example, we had basically all real numbers were the domain of that function. Now, what if we had a different function? Now we have f of x is equal to 1 over x squared minus 4. Well, the domain is implied to be the set of all real numbers for which the expression is defined. However, look that x is in the denominator, and if x is equal to either plus or minus 2, this function is not defined. It's undefined. So therefore, the domain for this function is all real numbers except plus and minus 2. Or written another way, x cannot equal plus or minus 2. Now I would like you to answer the following two questions and post the answers in the drop box. Okay? The first is to evaluate that function for f of minus 3, and the second is to find the domain of f of x.